Thank you for the introduction. So, hello everyone, my name is Jakob and I'm going to talk to you about enhancing construction data integration through dynamic ontology alignment and automated attribute mapping. So first, I wanted to start off with a very big and very prominent problem in the industry, and that is the cost of poor interoperability in the whole AEC industry. So when we look in practice, we will find that we have a lot of information loss and redundancy because the same information is stored multiple times in incompatible formats, which results in a lot of extra work and inconsistencies. And we also find fragmented classification systems. So for example, uniclass and omniclass, which are both classification systems that are used in construction to organize and structure information about buildings, materials, and processes. And uniclass we find mostly in UK and omniclass mostly in the US. So basically they have the same concept, but they are structured differently, and that results in difficult integration. And that leads to missed potential for automation. So without a shared semantic layer, AI systems cannot reason across datasets, which causes delays, data silos, and limited reuse of existing project knowledge. So to catch this a little bit more into numbers, we find several studies covering this topic. And one study states that we have, for example, $1.8 trillion in losses global-wide due to bad construction data. And another study states that we have $31.3 billion in rework in US construction alone. So we can tell that this is a very big and very prominent problem in the industry. So let's take a small step back and scale it a little bit down. So here we find, for example, an architect that basically creates an IFC file. So normally when an architect creates an IFC file, he inputs it into the IFC model, and attached to the IFC door, there are different kinds of attributes. For example, length, width is external, and so on. And what happens in practice is that the architect sends this IFC file to a door manufacturer. Mostly, these kinds of door manufacturers, and even the bigger ones, use in-house software solutions. So what these kinds of software solutions do is they extract the different IFC doors from the IFC that was delivered by the architect, and then the planning engineer goes ahead and start to work on it. So what they do is they generate a JSON and they start to attach their different components to the IFC file. They are not altering or modifying the IFC file itself, but instead they are generating the JSON which stores these kind of data. So to make this a little bit more simple, they tried the rule-based mapping. So with very simple and very transparent rules, but the problem in practice was it was very hard to scale and very labor intensive. So that was not the solution to streamline this process. So the door manufacturer, dormakaba, went ahead and they basically used the JSON, and they had attributes in the JSON, for example, the steel door frame, and they had attributes which were defined as has height and has width. So they basically used these kinds of data to create an ontology, which was nothing more than a structured framework that defines the relationship between concepts in a specific domain. And this is basically the standard that they used what the delivered attributes to the door manufacturer should look like. So we have on the ontology the definition again of has height and has width. And they did this because they wanted to facilitate interoperability across platforms and improve product search and selection. And the pro side of that is that it was very flexible, expressive, and machine readable, but the con side was it requires expert modeling and a lot of upfront effort. And if we look at in the industry in practice, we will find that still one major problem remains. So here we find different IFC doors delivered by different architects in different projects. So we have the first IFC door in the first project and another IFC door in another project, and on the bottom we will find the ontology with the definition what the door manufacturer expects the attribute to look like. So if we take a closer look, we will find here in the German IFC files attributes that are called nominale b mal h, which can be translated to nominal width times height, and on the right side we find attributes like Breite, which can be translated to width. So we will find here that this is not only a matching problem between different attributes, we will also find that this is a problem of different levels of aggregation, because here we find, for example, the attributes that is stored in a single line, which is obviously a fault. So we can tell that we basically have more or less the same attributes that are named differently, but we are talking about the same thing. And the consequence here is that we have a lot of data loss, misinterpretation, rework, and significant cost overruns. So this is why we came up with a system that basically solves this kind of problem. So on the left side, we will find different project users, for example, the architects, facility managers, and people in construction. And these people have different kinds of input data. For example, IFCs, PDFs. We are also using the BSDD and Excel files. And all these different kinds of files are inputted into an AI matching system, which uses natural language processing and basically extracts all the attributes and proposes to the system matches regarding his user input. Sounds very complicated. This is why I want to demonstrate it to you. So here we find the system, and when we fire up the system, we can basically input an IFC file. So at first I want to give you an overview over the IFC file. So here we find, for example, a school. And of course, in this IFC file, we find different kinds of IFC doors. This is one example, and on the right there is shown these different attributes in different languages that are attached to this kind of IFC door. So when we input this into the system, everything gets extracted. IFC walls, IFC doors, roofs, and so on, and all these different kinds of attributes are also extracted. And now we can go ahead and start to query the IFC. First we choose a user, and after that we can start to query the system. And we start with something simple like door. And now the system proposes the matches regarding to the user input. And the first match that we are finding is, for example, the attribute door material, and even more, the definition of a door, because the system understands this kind of attribute on a deeper semantic level. Now the user can go ahead and choose the proposed attribute and confirm the match. For our next attribute, we choose something like fire, and we find something like fire door, fire alarm zone name, fire protection, and what is even more interesting, something like extinguisher. So we can, again, choose a match, confirm it by the user, and basically train the system further. So the results of this system, we had, without any kind of human intervention, an overall precision of 86.6%, and with only 100 user interventions, we were able to push the accuracy to 92%. So this is the basis for the next step. So the key takeaway here is that AI-driven ontology-based attribute mapping demonstrate clear potential to improve data interoperability in BIM workflows. And on the next step, in the next upcoming papers, we will focus on the human-in-the-loop component to extend the system with role-specific interaction models, integrate adaptive feedback mechanism based on user expertise in project phase, and evaluate active learning strategies to balance automation and user control. So, thank you very much for your attention. If there are any questions left, I'm happy to answer them.